Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you can find information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer financial support to our students, please go to smarturl.it/help-ISU-actuary to make a tax-deductible donation towards our program. Here's a problem for today for exam LTAM. A pension plan uses the following multiple decrement model. State 0, a person is a member. In State 1, the person has withdrawn. In State 2, the person is on disability retirement income, disability income, so has withdrawn as well. It's no longer in the workforce, not a member, but disabled and receiving disability retirement income. State 3 is a person is retired because of reaching the retirement age, and State 4 is a person dies in service. Note that with the setup that we have here, States 1, 2, 3, and 4 are absorbing. Once you go into that state, you don't come out. Or maybe I should have said you don't come back to the to being an active member, but they're absorbing for the point of from the point of view of the model that we're using. So for the purpose of this problem. And you are given the following information. All transitions are modeled assuming constant forces of transition between integer ages. And the following excerpt from the multiple decrement table is given. At age 61, the population is of the size 58,622. 3,201 people withdraw during that year. 812 become disabled. 28,460 retire, and 413 die. And then at age 62, the active population is 25,736. And we are supposed to calculate the probability that 61-year-old transitions from State 0, being active, to State 1 of withdrawal within 0.6 of a year. A reminder, we're using a constant force assumption. That's how we can get this information about 0.6 of a year. Otherwise, nothing here would allow us to do the calculations for 0.6 of a year. But the constant force assumption is crucial, and it's constant forces of transition between integer ages for all of these decrements. And here's the solution. So, based on the data in the table, the probability of transition within a year from State 0 to State 1 at age 61 is 3,201 over 58,622, and that's approximately 0.054, 60407. The probability of transitioning out of State 0 to any of the other states at age 61 is the sum of all of the numbers of people who transition to any of the 4 absorbing states divided by the initial population. It comes out to be about 0.56098393. And then the probability of staying in State 0 is 1 minus that, about 0.43901607. Under constant force and multiple decrements, the ratio of the Q's is the ratio of the mu's. That's one way to remember this formula. Or in this case, because the Q's are probabilities of transitions out, the Q normally is the probability of death, but in this case it's the probability of moving out of the state of being an active participant. So the ratio of those Qs, which are P01 and P0, in this case, is the ratio of the two quantities we just calculated, 0.054604007 over 0.56098,393, but that's equal to the ratio of the mu's, which is mu01 over mu0, the forces that correspond to the probabilities of transition out. But also because of constant force, noting that states 1, 2, and 3, and 4 are absorbing, so that the probability of surviving to any state in any period of time of length t, of surviving in state 0 is the same as probability of continuously surviving in state 0 for the same period of time, because once you leave the state 0, you can't come back to state 0, so that's why these two probabilities are the same. And using this information, we can calculate 0.6 P6101 as the integral from 0 to 6 of TP6100 times mu01, although it would be 0, it should be 0, 0 with a bar above it for continuously remaining in that state, but we don't need to do this because those two are identical. So it's a probability of surviving in state 0 continuously for a period of time of length t, and then being whacked by the force of transition from state 0 to state 1. And we add it up over all possible times from 0 to 0.6, because we're looking for the probability of being whacked in that period of time of that length, whacked in the sense of being transitioned from state 0 to state 1, and state 1 is really withdrawal. So luckily no death here, just withdrawal, but anyway, it's the same logic. And that's the integral from 0 to 0.6 of e to the mu minus mu upper 0, which is the sum of all forces transitioning out. So it's a total force of transition out of state 0 times t. It's a constant force, so that's why we can just write it like this, times mu01 dt. And now if we factor out this mu01, which is constant, divided by mu0, then inside we can write the integral from 0 to 0.6 of e to the minus mu0 t times mu0 upper 0 dt. And now it's a standard constant force calculation. What's the probability of being whacked by constant force between 0 and 0.6? Well, that's the cumulative distribution function of exponential distribution with hazard rate equal to mu upper 0. So it's 1 minus e to the minus 0.6 times mu upper 0. Okay, but e to the minus mu upper 0 is the probability of survival for 1 year from all forces of transition out of state 0. So that's P6100. So what we have here is mu01 over mu0 times 1 minus P6100 to the 0.6. And all these quantities are now known. We plug them in, and we do the calculation, and we get approximately 0.03793948, which is answer A. Please remember, this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.